becomes important only when the electronic cloud around the nucleus, around the nuclei get distorted due to vibration or rotation. Vibration or rotation. It is very easy to visualize when it is in rotation. So let us take the example of H2O. H2O has this kind of H, O, H, H. Then you see that the charge cloud will be like this. Charge cloud will be like this. When this starts rotating around this, you see, O is heavy, hydrogen is small, so when I rotate it, I will not be rotating like this. My hand will go. Do you understand? My hand will go. When my hand goes up, the electronic charge cloud like this is different from the electronic charge cloud like this. Understand? So there is a change, distortion due to vibration or rotation. Under this condition, the center of nuclei, under this condition, you have omega is the laser, or this is the omega from the light, plus or minus m omega of molecule. This is the inherent frequency of rotation or vibration of the molecule. Then this is the instant light. The light may be ordinary light, it may be a laser light. So you will have new frequency generation because of the interaction between the light and the polarization produced by the rotation or the vibration of the molecule. Secondly, we put m because usually this is expressed in terms of Taylor series. M will be 1, 2, 3, but M1 will be stronger in all Taylor series. The first order, second order will be stronger than the third order. Under this condition, this is a general representation. Now what we are going to look at it, from this what is going to happen is, I send light, here is a molecule, it can be HCO2 or any molecule. So look at it, you will have light going here, 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 here. This is scattering. This is scattering. But the light which is scattered this side, you will have light scattered this side, light scattered this side. Always, light scattered in the forward direction is stronger than the light scattered in the backwards. So, forward scattering is stronger than, you can say, forward scattering, this is the backward scattering. Then, if I put an instrument, this is the detector. This is the detector. On the detector, I will get omega L. Let us put only one M. These are weak, so let us not bother about it. Yeah, the first step. So I will get omega L plus omega M, omega L minus omega M. Here I put M is equal to 1. Next step. Since I will have 3, how I get it, how I separate out. The simplest way, I come here. This is the forward scattering. I put a grating, or easy, I put a prism. Then look at it. I will have omega L. I will have omega L minus omega M. I will have omega L plus omega M. So I need a prism or a grating to disperse out. Disperse means separate out the frequency component. But look at, the forward light will be somewhere here. The light coming from the laser or from the light will be much stronger than these two. Or another way, when the experiment was done, this was so strong that you cannot observe this one. This you cannot say from the theory. From the theory, it will never say anything about that the light, this will be stronger, this is weaker. No, from the theory, you have no way of saying this one. But experimentally, the intensity of the instant light is much stronger than these two. So you cannot observe this one. So what you can do, next step. Experimentally what was done is this one. You take a mercury lamp, powerful mercury lamp, or this is, or you can take a discharge lamp from, say, copper arc. I don't know whether you have done any experiment with the copper arc. What kind of experiment you have done in your MS? Because it's a very common experiment. That's why I'm saying this one. You can do this experiment with 2 iron rod or 2 copper rod, any copper rod. All that you have to do is you connect to a high voltage battery. It's not a high voltage battery, it's a high current battery. This is connected. Now look at it. There is nothing here, so you will not get any current. All that you have to do is bring them together. Just touch. When you touch, it becomes conductive. It produces heat. Then you pull it lit. Then you will see, since there is a small gap of 1 millimeter, the field at this point and the field is so high, this will produce a discharge. This is called arc discharge, or this is called copper arc. Where have you seen this? Anywhere else? Forget even. Where have you seen this one? There is a place where you would have seen it. Do you go to cinema?
Yes.
You have cinema theater?
Yes, in Jordan.
You have cinema theater?
Cinema.
It didn't go. No cinema.
Why?
No cinema in Yemen?
In Sana'a, no cinema.
No cinema?
Yes.
Like this?
One cinema, but it was closed. No people go to cinema.
No people go to the... People does not care about cinema.
They have no money. They are poor.
It's different in Yemen. People doesn't have any interest to go to cinema.
Cinema is free, no problem. Anybody can go.
Ah.
But they have no money. They don't think about this thing. Only. That's just.
I see. That is very strange. In India,
In India, it's
people are
big
crazy.
in cinema.
No, I'm not joking. Everybody. Cinema is the most common entertainment. Everybody small baby, 1 year baby, to very old dying man will go and die in the cinema theater. Because that is in India, it's completely open country. You can do anything you want. Then all the people, after 5 o'clock, 6 o'clock, people will go, young people will go and play. All of them will go play. Football, volleyball, some, okay? Older people at the age of 50 or 40 to 50, they will all go to cinema theater. Almost everybody, you will not be, okay, everybody. After 50, 60, all of them will go to the temple or a mosque or church. You understand?
Yeah.
Then look at it. The middle-age group is so common. So every cinema theater will be always 50%, 60% full. And there are so many occasions you cannot get the ticket. Okay. Now forget the cinema. What is important for us is this one. The cinema theater, you have this one. That's what I am interested in. In any cinema theater, you have the projector. Instead of copper, the copper will produce a very bright, beautiful, bright, greenish yellow. Instead of copper, if I have carbon rod, you will have a very bright white light. You cannot see the brightness, it's so terribly bright. It will be like a real star. This white light, then the story is you put a lens, put your film, then you see the light passes through and produce the image here. If the film stops, the hero and heroine will be standing quiet. When it runs at certain speed, they will start running around. That's all the cinema, the whole point. Now, Raman made use of this idea. That's why I am interested. Raman took this lamp. Okay? Now look at it. Then, carbon arc or mercury arc. Then, put a filter. Then, you had light, very intense light at frequency, or let me see, omega. Then, this light is allowed to pass through a tube like this. This tube contained liquid like benzene. Benzene or a chloroform or any liquid. Benzene, let us say benzene, which is very common. Then light passes through and undergo Raman scattering in the liquid, which is a molecule for us, and then you will see, look at it, omega plus or minus omega m here, but if you look at this side, you will have omega m, omega L plus or minus omega m, but not omega L. You understand? Here you will have omega L and omega L plus or minus omega m. You will have 3 lines here, and here you will have mostly 2 lines.
Why we can't see omega in the down?
Because the light, this light is focused in this direction. So most of the light will go. But your question is right. You will always get some light. So what will happen is, you will have omega L, incident light. You will have omega L plus omega m. And you will have omega L minus omega m. You will have 3 lines.
in this direction, you mean? Or in that direction?
You know, it will be there in all directions. You can see here, 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 everywhere. Only thing is, if you look at this direction, the incident light is so strong that the scattered light cannot be detected at all. In this direction, still the incident light is strong, but it's not so bad. So you can detect all. You can detect here or here. So all scattered light is detected only at 90 degrees. This is true for fluorescence also. This is true for fluorescence also. Next week, same day, we will do all experiments. Then only you will understand the whole thrust of this, whole strength of my lecture. You will understand only when you should see it in the lab. Okay. Next point. Now, from all this description, you must get from whatever description I gave so far, I must get omega L plus omega M, omega L minus omega M. This and this is the incident light. This is scattered light, this is scattered light. Now these two should have same intensity. Both should have the same intensity. And this kind of shift is called a Stokes shift. Stokes shift. Why this kind of shift has been already observed by a British scientist called Stokes. In many stones, he was working mostly with the solids. He was able to observe this. This is called a Stokes. That is, this is the incident light. This is the light that with which he was able to see the another light. This again I can show you later. What is this? Suppose you have ultraviolet lamp. You know ultraviolet lamp? You have it in your lab. Ultraviolet lamp?
Yes.
Yeah. Take the ultraviolet lamp. Show any kind of dye or any kind of crystals. Okay? When you look at it, it will look ordinary dull color. When you look at with the ultraviolet, it look very beautiful, blue, green, yellow, red, so many colors. Understand?
Yes.
Now, point is, according to this scientist, he knows the wavelength of ultraviolet. This is about 350 nanometer. Yellow is around 600 nanometer. That means the incident light is 350 nanometer. The emitted light that comes from there has a large wavelength or small frequency. Understand? If this is 350 nanometer, this will be 600 nanometer. The frequency will less. And this is what he called a Stokes shift. Up to now, no problem. Next question comes. Raman observed this one. Understand? Raman observed another line which is a high frequency. You cannot understand. Not only that, this has intensity like this. So, look at it. Raman observed three lines. 1 omega L, this is the incident light. 2 omega L minus omega M, this is Stokes. 3 omega L plus omega M, this is totally new, this is called anti-Stokes. We call it anti-Stokes. That's the first totally different result. Second important result is intensity of laser incident light is much greater than the intensity of Stokes, which is greater than the intensity of anti-Stokes. This is called AS, this is called S, this is called incident light.
They have different frequency, and different intensity.
Yes.
Three or four, all of them.
All the three have different wavelength, or different frequency and different intensity. This cannot be explained from the explanation I gave so far. Understand? From all the mathematical equation I said, you cannot find any explanation. All this explanation given so far was based on classical theory. Classical theory according to the classical theory, you see this one. Yes. Look. According to the classical theory, if you remember, I started this equation something like this. Where is the equation? We started the equation P equal to mu naught plus alpha E, and then we went this one, and then we said, look at it, P is mu naught minus sigma n1 A dou mu by dou q n, etc., and you had cos omega mt plus something, right? This is the equation that you have. From this equation, this observation could not be explained. So what happened is, this is where Raman came in, and he gave the quantum picture, quantum aspect of photon and energy level of molecule. Energy level of molecule. In fact, the quantum aspect of photon has been already proven by Bohr's theory, already proven by Planck's theory, Einstein theory. So, this is up to now there is nothing. Planck plus Einstein have said that light is a quantized particle. Then look at it. Bohr said the energy level of atom is quantized. Okay? Only under this condition, you can explain hydrogen spectra, which you must have studied in the school. Hydrogen spectra, when you observe the hydrogen spectra, you get lines like this. This is possible only when this is the nucleus, you have the energy level K, L, look at it. In between there is nothing. The energy levels are discrete and quantized. Now look at this one. this is the atomic picture. For the first time, Raman said, this is the atomic energy level or electronic energy level. Now, Raman said, energy level of vibration and rotation of molecule is also quantized. Is quantized. Only then you will have one light, this light, and there is nothing. You see? That's the first step. He got half his Nobel Prize. Then you see the next point. That's where the whole beauty comes. This one, this Stokes line, then look at it. Intensity of laser incident light is greater than intensity of Stokes, is greater than the intensity of anti-Stokes. So, this is Stokes, this is anti-Stokes. It is very small. For this, Raman gave a very fine explanation. He said, imagine the molecular energy levels are discrete. First thing. Why discrete? Look, the spectrum are discrete. First step. Secondly, you call this as the lowest electronic energy level, E1. You call this as the higher electronic energy level, E2. This is how he built the molecular energy level diagram. And then he said, something like this one. Incident light, let us say this is the light of light. It goes and comes back. Remember, this will not go and touch this one, because if it goes from here to touch this one, that becomes absorption. Absorption is different from scattering. Absorption means from here it goes here, stays there for 1 or 2 nanoseconds, and then it undergoes certain relaxation and produces fluorescence. You have studied something about fluorescence?
Studied, yes.
I have taught you laser spectroscopy, so I would have told you. Do you know anything about fluorescence or not?
Just last semester I read something about fluorescence. When we talk about cancer, how the fluorescence. About how fluorescence is found? How the fluorescence consists? Inside the molecule?
No. Yeah. Leave it for a while. I will explain what is fluorescence. Then only you will be able to understand Raman. Imagine a molecule like benzene. Benzene is common, that is what you see in your petrol. The molecule, the representation of this is this. Benzene, this is CH, 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 CH. And then you will have bonds like this. This is called pi bond, pi bond, pi bond. This is called the sigma bond. I don't want to go into the details of what is a sigma bond or pi bond. That we are all going very much away from our discussion. Imagine that it's this represents a molecule like benzene. Then compare the energy level of this with hydrogen. And for hydrogen, look at this. This is the nucleus. This is the K shell. This is the L shell. So the energy level will be K L, M, N. I am not talking about hydrogen molecule, hydrogen atom. All the energy levels are well defined, clear. Whereas here, you don't have one atom. How many atoms? This is actually, this is C6H6. C6 means each one will have how many electrons? 6 electrons, right? Yes. 6 electrons. This is having another 6 electrons. There are 12 electrons in total. 12 electrons. No. Sorry.
36?
Sorry, yeah. This will be 36 electrons plus 6, 42 electrons and 12 atoms. Understand? A benzene molecule has 12 atoms and 42 electrons. If we build the energy level for benzene, you can build like this. See, in K shell, you have 2 electrons like this, right?
Yes.
In L shell, you can have how many? Totally 8 electrons.
8.
You know the rule.
8,
So
yes.
this will be 8 electrons. And here it will be like this, I
18.
think 2n square, right?
18.
18. Okay? 2n square, like n square. Now look at it. If I try to build like this, I will have totally 42 electrons. But the most important point here is, even though you say 8 electron will live in 4 houses. Am I right?
Yes.
One spin up, one spin down. It is something like this. This first floor, it has 4 rooms. In each room, you have husband and wife live. That's all. 2 people, nothing more. Here you have many floors. Here there are, in the second floor you have 9 rooms. In 9 rooms, 9 into 2, 9 couples live, 18 people live. Same way you come here. 42 electron means you will have 21 orbits, okay? 21 flats. You must build up like this. Now look at it. Second point. If you consider this, from here this will be big, here small, here it is small. As you go up, energy level come closer and closer, right? Keep the same thing, come here. You will have 21 rooms, so you cannot have a tall building. The building will be small, the building has to be reduced. Not only that, the height of the room has to be reduced. Understand? You get the picture?
Yes. They're close to each other.
See, look, here you have only few, so you will have, I built a multi-story building with 1, 2, 3, 4, only 4 floors. So I can have a big building with the tall rooms. But here I have to put 21 flats. So I cannot have this one, so the energy level become close. That's the point. Now look at this one. All put together, I can say, look at it, this will be the, you can say the spin will be paired. This represents the lowest energy level, E1. This is called S1. This S0. This is called S1. There is a reason for all the S0, S1. That all depends upon molecular orbital, and it is pure molecular spectroscopy. Maybe you must have studied. I don't want to go into the detail. Then you will forget later. What is important for us is this. Imagine these are the energy levels for benzene molecule. Then I send a photon, H nu. The molecule will be always in the ground state. These are called vibration levels. V0, V1, V2. V0, V1, V2. These are electronic energy levels. the photon takes a molecule from here to here. This whole process takes place in 1 picosecond. In fact, this is done even faster. The whole jump takes place in 100 femtosecond. Then, from here, it comes down, producing vibration, and comes down to this. And from here, it cannot go down because there is a big gap. There is no staircase from the first floor to the second floor. So, from here, the molecule will jump down, producing fluorescence. Immediately you can see from here to here the absorption takes place at a smaller wavelength or larger energy, and the emission takes place at a lower energy or a longer wavelength. For example, if this takes place at 400 nanometer, or let me say 350 nanometer, which is the ultraviolet light, with which Stokes did a number of experiments, the light that comes out will be 400 nanometer. So incident light is ultraviolet, emitted light is visible, longer wavelength. This is defined as fluorescence, or lambda of fluorescence is always greater than the lambda of absorption. Now, next point. This fluorescence takes place within a time of about nanosecond. 1 or 2 nanoseconds, 5 nanoseconds. This is true for most of the gases like benzene, like liquid like benzene, and also true for some solid. But next thing, in solid, you have one more thing. The molecules which come here can go from here to here, another energy level which is called T1. This is called a triplet state. If they go on to this state, from here they cannot come down so easily because it is a forbidden transition. Since it is forbidden, from here you will have a very weak light and a very slow light. This is called phosphorescence. This is called phosphorescence. Where have you seen phosphorescence? You see it so every day. Where have you seen phosphorescence? You are all very familiar. Perhaps you do not notice this one. You sleep and the alarm wakes up, right? You have seen many alarm will have a green light, alarm clock.
Yes.
You have a green light in the.
Yes.
If you switch off the light, you can see the green.
Yes.
That
yes.
is phosphorescence.
Because you will find it to switch on.
You know where is here it is. Yes, you want to make it quiet. Keep quiet. I want to sleep, right? That has some kind of solid paste made of this kind of material. So it will emit light, a very weak light, but you will see the light even in the dark. That is phosphorescence. Also, I don't know whether, when you switch off the TV, have you seen something funny? Okay, when you switch on the TV, what have you seen? Something strange.
The screen.
You will see the, imagine that you know some channel, okay? Yes, just switch on. First you will hear the sound, only later you will see the picture. Understand?
Yes.
Let me repeat, then you will understand. You know light travels faster than sound. When there is a lightning or a thunder, you will see the lightning first, thunder comes very slowly.
Yes.
Whereas in the TV, when you switch on, you will see the sound first, only then the light comes. Not only that, when you switch off, first the sound will go, but the light will slowly go. You know the reason?
Yes.
All these are due to electrophosphorescence, right? The light is produced on the screen. You see the light on the screen, which is phosphorescent. So light hits electron hits it, produces light very slowly, and takes the light off also very slowly. You can check this today, switch on and off. You will see the beauty. Yes. Now comes Raman. In Raman, this is fluorescence. The transfer is from one quantum state to another quantum state. Fluorescence is possible only when the molecule absorbs and re-emits. In Raman, the molecule is not absorbing. The light goes, then it cannot go here, it will come back. Because look, nothing happened. So the light has come down. The light comes down, so this gives the incident light and the scattered light both have the same wavelength, so this is what you call scattered light. And this kind of scattering is called Rayleigh scattering. I don't want to put R alone because Rayleigh, Raman both have R, but this is called Rayleigh scattering. That is scattering without change in the wavelength. Next step. This is how Raman pictured it. Take the same molecule, do the same experiment, look at this. It goes and stop here. If it stops here, the scattered light has lesser energy or more wavelength. So this is called intensity of Stokes light. The third picture is, look at it. We don't change anything here. Only thing is the light goes. Now, suppose the light starts from here. It starts from here. It will go here. Because it starts from here. Then it comes here, and comes here. Then you will have intensity of anti-Stokes light. You understand three pictures?
What's this mean if it starts from the lowest, the second? What's this mean?
Here, light is coming here.
Yeah.
Molecule is here. The molecule gets affected by this light, and the molecule goes, and comes back to the same place.
Okay.
In this case, the molecule did not get energy, did not give any energy. So the incident light and the scattered light both have same energy, same frequency, same wavelength. This is called Rayleigh scattering. Next step. Do the same thing for certain molecule. You will see it starts from here, but this photon stop at a higher molecular energy level. Then this much energy is lost.
This infinite.
Huh?
The isotopes have.
This explains a scattered light which has lesser energy or longer wavelength. This is called Stokes light. Here, imagine the molecule is already in a V is equal to 1. This is V is equal to 0. This is V is equal to 0, V is equal to 1. Okay. Then it goes, comes back. Okay. But when it comes back, the molecule gives some energy for the radiation. So the radiation has a higher energy or a shorter wavelength. Understand? Now this explains. So out of these three, which is more common? All the three are possible from this explanation.
Raleigh.
This will be more common. This will be less common. This will be least common. Understand? I'll give very good example. You will understand. Suppose there is a earthquake, or suppose flood is there in India. Okay? I want to send 10,000 riyal to some people suffering in India. A friend is saying, a friend is going, I say give 10,000, give to the poor people who have been affected by flood. My friend gives 10,000 riyal, okay? This is one possibility. Another friend, I gives him 10,000, he gives 9,000 riyal, takes 1,000 riyal, put in his pocket. Imagine one more condition. I give 10,000 riyal, but that friend gives 11,000 riyal to the poor people. So you have three conditions. Which will happen more often?
10. The first one.
Most of the people will say, whatever money you gave, I will give to the poor people.
Yes.
Very few people will take the money from me.
Yeah.
And very, very little people will give more money.
So,
Understand? This is exactly what happens.
This is a good example.
Yes. This is real example. I will give another example which you will never forget. You are all married, so you will. The difference between fluorescence and Raman is like this one. Imagine you are walking in the airport, okay? There is a very beautiful girl. You give a bouquet. Don't try. You are all married. You are coming already jailed. Okay. You give a very beautiful bouquet. If she accepts and smiles, this is something like a fluorescence. Understand? She accepts, smiles, or suppose you say I love you, she accepts and says smile, and she say I love you. You gave something, she gave something in response. You see, there is a time delay between giving and responding. That takes place in few nanoseconds. On the other hand, look at it. That woman, she speaks, let us say, Chinese language. I speak in Indian language. She is really beautiful. I like her and go. She will not understand what I am saying. Understand? She will say, go. She will go away. Understand? So I will come back. The response is very fast because she will never understand what I say. She will not get angry also. She will just go away. Okay? The response is so fast, I will have my bouquet with me. Understand? I did not lose anything. Imagine I do the same thing with the Arab. I know little. Okay? Then what will happen is, from what I say, she may understand and they say, sorry. Understand? She will go away. Okay? On the other hand, suppose that woman is a Korean woman, North Korean woman. She is already very angry. If I go and say something, she will give me a slap. Get the hell out of this one. Understand? This is what. She gives extra energy instantly. No time. Understand? This is wrong. Out of the three, this is what will happen most often. Most often, no. You are asking something. I have no time given to look back. Understand? This is scattering. The time spent here practically nothing. Here time is few nanoseconds. Few nanosecond is very big in these days, because later I will show you, I work with the femtosecond lasers. Few nanosecond is a long time for me. Okay. And then next, then you will understand the whole idea. What Raman said is, look at this one. Suppose there are come back, this picture. This is the picture Raman built. This is V is equal to 0, V is equal to 1, V is equal to 2, V is equal to 0, V is equal to 1, V is equal to 2. These are electronic energy levels, so I call it E1, E2. These are vibration energy levels. Then, let me calculate the population or the number of molecules in this level, in this level, in this level. Then look at it, E1, V1 over E1, V0 would be delta E K T exponent, what is this? Exponential minus delta E over KT. What is this rule? This is Boltzmann distribution law.
Yes.
Boltzmann distribution law. For example, you can take it as a homework. The energy separation between these two, let us say this is about 1000 centimeter inverse. Take this as a homework. 1000 centimeter inverse. You can measure the energy separation in joule or in erg or in electron volt, but in Raman spectroscopy we measure in terms of centimeter inverse.
From this we can know the number of molecules in V1.
That's all. You understand? Now from this you find the ratio. You don't have to know this one. This ratio, that is number of molecules staying here compared to the number of molecules staying here, will be 0.1. That is, if I take 100 molecules, 99 molecules will be here, only one molecule will be here. What does it mean? That means, come back here. If I do this experiment with the 100 molecule, then what happens? 50 molecule will go and come back, produce light by 50 molecule. 20 molecule will go and come back here, produce less vibration, energy of less molecule, less energy. Only very, very few molecules will be here. Only one molecule will be this one. So, only one molecule, which is already angry, will give the energy to the incident radiation. So, only a very weak light will have energy greater than the given energy. Understand? And this is quantified. This is you can measure this one. This gave a very proper explanation from the quantum physics. The complete picture of experimental observation was given by Raman using all these arguments. Just for all these arguments, I think he did this experiment February 25th, I remember, 1928. This is an important day in India. This we call as a Science Day in India. For this he got Nobel Prize in 1930. Now why I am saying this? He was the first Asian to win Nobel Prize. Then it took, what is this here? put it this year. This is the first time an Arab won a Nobel Prize.
Very.
Long distance, you understand the big difference? 72 years it took for Arab scientists to win a Nobel Prize. Again, he is Albert Zweil, Hermann Zweil from Egypt. He did his BS degree in Egypt, MS, PhD. Everything he did only in USA. Okay? Whereas this Raman, he did everything in India. He never went out. But he was so good. He had that kind of intelligence, very smartness. So he did all experiment, all modeling, all explanation in a small laboratory, which is only this much. That's all the size of the laboratory. Okay.
Yes, good mind.
Yeah. The next interesting thing is this. As I told you, Raman experiment was very simple. This is an arc lamp, put a filter to choose a particular lambda. I will show you one such filter later. You remind me. I will show you all this in the laboratory. Then you put a lens, focus on the tube, then you collect the light here, and then you put a grating here. Here you have a photographic plate, then you had a like this. That's all the whole experimental setup. This was done in 1930. Then 1930 to 1950, people did a lot of research in this line. And then people forgot. Why? Because it has no value at all. It was a good experiment. He got Nobel Prize, very good. The funny point is Raman put all the money in a bank, the Nobel Prize money. That bank disrupted. They said no money.
Really?
Really, I'm not joking.
And
The bank broke. Then he went to the government, he cried, look, I'm the one Nobel Prize winner. I got so much money, okay? I put in this bank, and the bank said no money for me. I mean, the bank closed. Okay? Then, fortunately at that time, British government was there. It was the time British government was there. That government catch hold of the banker, gave him a lot of slap, asked at least give money to this person, okay?
At least to the...
To the scientist, he got the money, at least 50-60% of the money. Then he built another research institution in India, Bangalore, that's called Raman Research Institute, but it is doing very well. Now, let's go to the next point. After that, people have forgotten. They don't know what is the application, what is the use of this one. Okay? Then what happened is, all this because, look, you need to have very powerful light, keep on producing exposure for a long time. What I mean to say, the time required to do this experiment is 10 hours, 20 hours. Sometime people, Raman even used to say, I put all this experiment, go and visit my friend's daughter's marriage and come back, only then this experiment is done. You understand? It took 2 days.
Because they used the